Okay, great. Good afternoon, everyone. Angela and I are very happy to have you join this session. We will be talking today about interrupted time series analysis with individual level data. We'll talk a little bit about what is interrupted time series analysis, or ITS as we call it often. When is it appropriate? When it can be used? Like what are the questions that may be answered based on this type of analysis? We'll go through some examples. We'll talk about the strengths and the limitations of ITS analyses. We'll focus mostly on individual data, but we'll also talk about aggregated data analysis. And finally, we'll summarize what we've discussed today. So what is an interrupted time series? It's essentially a longitudinal data set on a particular outcome of interest. And it's used to, a longitudinal data set that has been interrupted at a known time point. It's also known often as segmented regression, because essentially what we're doing is that we are assuming that there is a trend before the intervention and a trend after the intervention. And it's used, ITS analysis are used to assess the intervention of a population level change or a protocol change, or any kind of change at a high level. For example, at a given hospital, there might be a protocol change in the way asthma exacerbations are treated. For example, that's one of the examples that we'll go through, in which at the University of Colorado, there was an protocol change in the way asthma exacerbations, or I think might have been other respiratory infections, were treated. So essentially, we would want to see whether there is an effect of the intervention because of the change. So when can we use ITS analysis? When we know the timing at which the intervention occurred. When we have well-differentiated pre-periods and post-periods, so that we can say clearly, like, this was before the intervention, this was after the intervention, and also when we have sufficient data. As you can imagine, if we're trying to fit a trend before the intervention, we need to have enough data points to fit that trend in a reliable manner. When it's ITS, it's better to use when we have a short-term, a relatively short-term outcome. And the reason is because if the outcome is long-term, then it's going to be much harder to make the case that the changes in the outcome are due to the intervention. If we have to wait a long time, because there might be so many other things happening at the same time as the intervention occurs. Changes may be evaluated in an immediate effect, or an immediate change in the level, or a gradual change. So a change in the slope. For example, if we look at these figures, the first one, A, is we have an immediate change in the mean level of the outcome. You can see here at the time of the intervention. But notice that the slope is the same before and after, right? The rate of change seems to be about the same. In B, we don't have a mean level change, an immediate change, but we have more of a gradual change. In C, we have both, really. You can see that the slope is also changing after the intervention. The next one, we seem to have a bit of a lag effect. So there was a change in the protocol or yeah, the legislative change at the time here of the intervention, but then we don't see a change until much later. So this is a lagged effect. The next two are, well, the next one is a temporary change in the mean level, and the last one is a temporary change in the slope. Now, the very basic or a very common model is as we'll discuss in this slide. And as in many models in biostatistics, we can parameterize the model in different ways, and that's perfectly fine. It's essentially the same model, it's just parameterized in different ways. So for example, here we're modeling the mean outcome as essentially a linear model that depends on a binary indicator of the pre-intervention period and the post-intervention period. That's the variable X. And we have time, and notice that we have the interaction between that binary indicator for the pre and post periods, and we have time as well. So the interaction of those two variables. And what that means is that this interaction is going to allow us to have a different trend after the intervention versus before the intervention. So we can ignore, if we think about the trend in the pre-intervention period, that would mean that these two terms disappear. So what that means is that then we have this simple linear regression model in which beta naught is the baseline level at time 0, and beta 1 is the slope or the rate of change with respect to time. So that's what we're saying here in the pre-intervention period. Now, if we look at the post-intervention period, then beta 2 is going to be the mean level change. So beta 2 would be this distance, the mean level change in the outcome, and beta 3 would be the change in the slope following the intervention. So we can write this out fully and interpret this way. And as I said, we could also parameterize this model in a different way. For example, we could assume that there is just one mean trend or mean slope across the entire period, and then we could distinguish the the slope in the pre-period and the slope in the after period as summing, or as the difference from that overall mean trend or slope. So Angela will go through the examples and then we'll.
Great, okay. All right, I unmuted myself, right? You can hear me. I'm going to talk about 3 examples here of an ITS. The first one being a study done by Amy Tyler in 2019, where she looked at comparing outcomes pre and post a protocol change that occurred here at Children's Hospital. The protocol change occurred in the ED department, and it involved the adoption of dexamethasone over prednisone for the treatment of acute asthma exacerbation. The cohorts were kids that were admitted came to the ED and that were then admitted to the inpatient part of the hospital for acute asthma exacerbation. We did use individual level data for this analysis. We did have subjects that came back over time, over the course of, I think it's just a little over 2 years for this data. And we used logistic and log gamma models for the outcomes. We had 3 main outcomes: length of stay, ICU admission, and then the third one, which is you don't see here, was cost, total cost for admission. If you look at the 2 figures on the right, they're examples of like an upper time series, a classic figure for it. You have the outcome on the y-axis and then time on the x-axis. The noisy line in the background there is the observed values that were summarized in the monthly time period, so per month. And then the model results, the predicted model results were summarized and graphed on top of those. And that's the red line that you see on top. And in both cases, you don't see, in this particular study, an intervention occurring, meaning a sudden drop, an intervention effect, a sudden drop occurring in that post protocol change period. Maybe a little bit of a slope change. And keep in mind that these are unadjusted analyses that have been modeled and graphed up. The reason why we did do this individual level data was because we wanted to adjust for individual level covariates, such as age, race, financial class. We did adjust for season 2, admitting service, first asthma score, and need for continuous albuterol. So once we adjusted for those, we still saw no significant immediate differences. But the one thing we did see was that ICU transfers, which were stable in the pre-protocol period, were now increasing by 10% per month in the post-protocol period. Elizabeth, can you advance me a slide? Yep, here's the next example. So this was Ferrante 2012 paper. It's a study that came out of Argentina regarding smoking bans that occurred there in these 2 different regions of Argentina. Santa Fe did a complete smoking ban, no smoking in public places. It occurred somewhere around August of 2006, whereas Buenos Aires City they did a partial one. So they restricted smoking to certain places in bars and restaurants, and they added filters and so forth. And that occurred somewhere in October of 2006. This is an example of population level data. So they aggregated their individual level data into months and then did the model on top of that. So they use multiple linear regression techniques, which I take to be some kind of segmented regression, probably analysis here. And they use age standardized acute coronary syndrome emissions as the outcome. So they're looking at smoking ban on how it affects acute coronary syndrome emissions. They did adjust for a seasonal trend. The graph you see on the right here is just observational data. So the monthly data observed. And even at this level, they didn't put model results, but even at this level, you can see things happening here. So you get an idea of what you're going to need for your model. And when they did do the model, they saw that Santa Fe did have that immediate change. So Santa Fe is the one that had the full smoking ban, the black line, black dots you see. They had an immediate change post ban, and they had that change did persist, meaning that it continued to drop over time in the post period. Whereas Buenos Aires, the gray line, didn't see any effect. They're the ones that had the partial ban. So that didn't seem to affect the acute coronary syndrome emissions. All right, let's look at the third example. Okay, so this is, I'm gonna spend a little more time on this one. This was Dr. Lockwood, Justin Lockwood. He looked at the association between legalization of recreational marijuana and birth outcomes in Colorado. It's another 2019 study. He had birth certificate data for all live births in Colorado between 2012 and 2016. So it was a large data set, about 270 births, 70,000 births. And he also was able to obtain marijuana retail license counts per county for the state of Colorado per year. His outcomes that he was interested in were small for gestational age, and that's defined as birth weight less than the 10th or in the lower 10th percentile, and NICU admissions for infants born after 35 weeks. We did look at including an additional exposure variable. So we did this analysis with and without this additional exposure variable. I wanted to present it with it just because it's more complicated and more interesting analysis, in my opinion, model. The additional exposure variable looked at, well, we did it as a surrogate for marijuana exposure for the mothers based off of the idea that you're assuming increased risk with closer proximity to your source. So MAUD, or marijuana outlet density in maternal county of residence, was divided into 3 categories. Either they just didn't have any marijuana retail stores in 2015, and they were considered in the none category, or they were divided up between low and high at a median value of 17 retail outlets per 100,000 in the population. We did do this at the individual level as well because we wanted to control for individual covariates again. We looked at bivariable comparisons between the pre and post period. And even though this is a really large study and everything was significant, we did see some clinical differences that we thought were important to account for. So covariates included maternal age, race, ethnicity, education, hypertension, elevation, and smoking during pregnancy, drinking during pregnancy, and early prenatal visits. Elizabeth, yeah. So here's a look at what the intervention looked like. Marijuana was legalized in November of 2000, and then 12 years later, recreational marijuana was legalized. Then the dispensaries opened in 2014, January 1st of 2014. So we are considering the intervention occurring when the public could get access to marijuana, which was when the dispensary opens in 2014. We have data for 2 years before and data for 2 years after. Okay, let's go to the next slide. All right, this is an idea of what the exposure looked like in 2015. We're going to use the year 2015 to get a good idea of the marijuana exposure for the mothers. The darker colors are considered those that were the high mod counties. And then the medium ones, low mod, and then of course the none counties, the counties that didn't have any medical stores were the lighter colors, and they accounted for about 50% of the 64 counties of Colorado. All right, let's go to the next one. Okay, so what's that model look like? Here it is. It's similar, that first line of the model, similar to what Elizabeth just showed you, the basic model, but then we're adding every intervention that we can think of. T is the time elapsed from the start of the study. X is a binary variable indicating what legalization period it was. Z is an exposure variable for the 3 levels of exposure for the mod counties, high, low, or none, where none is the reference. And then we have that vector V, which is going to be all our individual level covariates. The analysis plan here is to remove a washout period first, right? We don't want any overlap of pregnancies from the pre-period into the post-period. So we're removing the first 9 months of 2014 from analysis. And we're going to do a simple logistic regression, aggregate those predicted values that come out of the model by month and graph those on top of the observed values. So we get that nice ITS figure. Then we can add in the covariates to the model and get a multivariable logistic regression. And those results, we can look at those results. All right, the next slide is a figure, the ITS figure for small for gestational age outcome. So the x-axis is going to be the percentage of SGA births, overall births for that time period. And of course, X is time. And then you've got your noisy background here, which would be observed values. And the straight lines are going to be your predicted aggregated values by month that come from the model. And the thing to note here was there was no intervention effect. So that particular period of time, that pre to post, it doesn't look different. But what is interesting here is that there is an exposure occurring and it's occurring pre-legalization as well. So that's interesting. And it sparked a lot of discussion. Let's go to the next slide for NICU. So once again, NICU, this NICU is the outcome emissions. Here you can see an intervention effect occurring, which means if you look in the post period, the slope, there's an increased NICU admissions. They're just getting greater per month in the high and the low group. Whereas in the non-density counties, there doesn't seem to be any intervention effect at all. Okay, and those figures were for the unadjusted results. Now this is a table of the adjusted results, adjusting for all those individual level covariates that I listed before. These are the outcomes here. The third column here is odds ratios and the 95% confidence interval. And usually in the ITS studies, you want to present your trend pre, your trend post, and then that change that you're interested in at that time point, which in this case is the first time point post legalization. The thing to note here about the SGA model is that even after adjusting for covariates, we still saw that exposure effect, those last 3 lines where there was a difference in baseline risk between the high and low, the high and none, and the low and none categories, or mod, count, and counter categories. So that still existed even after adjusting for other covariates. Let's go to the next slide, NICU. Okay, so this is odds ratios as well. We're seeing that increase. If you look at the low group, the low store density counties, and the trend post, you'll see that it's significant, 1.01. And that is, those confidence intervals are really narrow because this is a very large population here. And the high group is also, that's even more significant, well, a greater odds ratio. So what it's telling us is that NICU, after adjusting for all these covariates, that NICU admissions are increasing at a greater rate after legalization of marijuana. All right, let's go to the next slide. Okay, so this strengths of ITS. ITS is great in evaluating for intervention effects like that level change and the trend changes pre and post, while controlling for your underlying time trends. It is, this is time series data, so you're able to assess whether that intervention is short-lived or it's going to be sustained over time. And I think the greatest thing here is to note is that it can be done with either population or individual level data. So you often, I think it's more traditional to see it done with population level data, but in times it's necessary to use your individual level data. You can account for time varying confounders, and you can get a control group. That figures that I showed you, those are great because they're intuitive visual display of results. They help with facilitating the analysis, as well as communicating the results to others. The longitudinal nature of the data, especially for the population data, allow these populations to act as their own control. So you can use it with smaller populations. You need more time points, but smaller populations don't seem to be as much of a problem. And one, it's both on the strength and weakness list, would be the use of interactions and segmented regression. So the more interactions, the more complex you can get, which allows for more flexibility. You can add in more interventions, you can add in more time periods, pre and post interventions, and you could add in groups, control groups, exposure groups, and compare between them using interactions. Let's go to the next slide. Now here's some limitations of ITS. As Elizabeth said, you need stable data and you're gonna need a large number of time points. The rule of thumb is usually around 8 to 12 time points for population level data. And it's very hard to find a control series because we're dealing with a population level intervention. So you want a control series that's not affected by that population level intervention, but is extremely similar to your experimental population. When used in population level data, ITS cannot be used to make individual level outcome inferences. And it is challenging with rare outcomes because you might not have enough data to measure those trends and compare them. It sort of goes along with the need for stable data there. There's no graphical representation of an adjusted model here. And the interactions, this is where I'm considering part of the limitations here because interactions can just be difficult. They can be difficult to design, they can be difficult to estimate, and they can be difficult to present and to communicate. So the take-home message there is just have a statistician work with one to do that. There are threats to internal validity that you needed to consider when you design an ITS, and you go to discuss this in your paper. or pick your data. Factors other than an intervention may influence the outcome. Like we saw some exposure effect occurring in that marijuana study. And one idea is that maybe opioids could be affecting it. The use of opioids and how they're changing over time could also be affecting the outcomes there. So that's a co-intervention or competing intervention that we weren't able to measure. Changes in the ability to measure the outcome or missing data can have an effect on getting or establishing your time trend. And there's also an issue with selection bias, where you end up with an intervention group or post-intervention group that differs in the pre-intervention group and their characteristics. So that's an issue. And then, yeah, Elizabeth, I think I'm ready to turn it back over to you.
Right. Yes, great, Angela, thank you. So ITS, as we were saying at the beginning, may also be used with aggregated data. It is nice to use individual data if it's available, but sometimes that's just not possible. And particularly, I would say in econometrics, it's very common to see it used with aggregated data. And essentially what we're trying to do in that case is to model the averages over time or rates or proportions. And the usual or almost the same issues come up as with individual data, but some that I would say are particularly more important in this case of aggregated data is one, serial correlation, particularly if we are just summarizing the data at the population level. They're very likely, if we think about a proportion, for example, proportion of the use of certain medication, say in the ED, it's very likely that the proportion for a given month or a given period is highly correlated with the previous month or the previous period. So autocorrelation is an important methodological issue that needs to be addressed. I would say in aggregated data, it has to. There may also be a seasonality effect, and there could also be a seasonality effect in like individual data, but but we might not necessarily be so interested in that, and we can always, we can model that without any problem. But I would say in this case, it might be more common, again, because we are looking at rates or proportions or averages at the population level. Stationarity is another problem. So the idea that we have here the same mean and the same variance and the same serial correlation over time, that's the assumption of stationarity. So if that doesn't hold, then we need to address it in some sensible way. Covariates, if we want to adjust for covariates, then that means that we need to have covariates at the aggregate level. And as you can imagine, in some cases, that's challenging to do because one, we need to come up with a covariate at the aggregate level that makes sense. And also we need to have the information to calculate that covariate. Also another challenge that is probably more specific to aggregate data analysis is over dispersion. Since we're dealing with proportions or rates here, it's very common to have over dispersion in the data, which is this phenomenon of having a larger variance than the model can account for. Now, there are other methodological considerations that we wanted to mention here as well. And these are common to both individual and aggregated data. One is that much more complex modeling may be used, for example, in using generalized linear mixed models or generalized additive mixed models, which are essentially just smooth models that also allow for different or complex structures of correlation. And as we mentioned before, with aggregate data, models that address serial correlation. like autocorrelation or ARIMA models. Another issue is outliers. Particularly, well, outliers are always important to check, but particularly with aggregate data, and if we only have a few time points, it might be more important to check for this, or yeah, just to do a thorough analysis of outliers, because if you only have a few data points, say Angela was saying that the rule of thumb is often thought of as 8 to 12 data points before and after, 8 to 12 before and 8 to 12 after. But say that you only have those time points, 8 or 10, and you have a few outliers in one of your data points that might be driving or influencing the results more than we would wish. So it's just something to be careful with. Now, missing data is another consideration, which it might come up more for aggregate data, particularly if the patterns of missing are different over time. And then we're not aware that really the outcome is also reflecting, or is primarily maybe reflecting, those patterns of missing. Then we might have some sort of trend that is not really due to the outcome, but more missing data. Another point to consider here is that there could be a control group observed over time, which is extremely helpful when we're trying to make inferences about whether the intervention had any sort of effect in the outcome. And often, or not necessarily that often as we wish, there might be a control group that we can consider. This analysis is referred to as difference in difference analysis, and is as you can imagine, is a much stronger design than not having a control group. And this falls within the area of causal inference, and there is there's a ton of research in that area, and a lot of very complex designs to address the question of whether there are any differences in the intervention arm versus the control arm. And then, as you can imagine, like once you put it within the framework of causal inference, then there is propensity analysis, there is more discussion and more methods to address selection bias and all the issues that come up whenever we're trying to answer a causal question. And finally, just to summarize, so ITS is a powerful, strong quasi-experimental approach for evaluating longitudinal effects of interventions, with the caveat that there might be other factors that could influence the outcome. So I would say that's the biggest threat here that one has to be careful with. That there might be other things that are influencing the outcome beyond the intervention, and that's something that we can't necessarily check. ITS allows for considerable design flexibility. As Angela was mentioning, this could be extended to having multiple interventions. So you just add segments to your regression model, right? As long as you know the timing of when the intervention is implemented. There could be time varying covariates, and if we are able to use individual level data, it might be easier to deal with those time varying covariates in that framework. It also allows for addressing serial correlation, which is particularly important for aggregated data. It allows for a series of modeling techniques that address multiple important aspects of the study design. And that is the end for us. Are there any questions? We do have one slide that we could go over if people don't have any other questions. So here's some SAS code of the example that Angela presented on the marijuana study. If there are no questions, we thought that there might be interest in discussing the differences between individual and aggregate data analysis using ITS techniques. And so, for example, if you think about autocorrelation, we will say that it's more important to address in aggregate data. In individual data, often you use different individuals, so there is no need to worry about breaking the independent assumption of linear regression. So we would say that you definitely need to consider autocorrelation here. So we were thinking about that as a disadvantage. So we would put a minus in here, but another way of saying this is just something that it needs to be addressed in this case. Seasonality and stationarity also very likely needs to be addressed for aggregate data, but not an issue for individual data. Confounding, both, really needs to be addressed in both. And that again depends on the variables that are measured. Missing data, addressed in both, but if there are differences in terms of missing patterns, it might be more of an issue for aggregated data than for individual data. Clustering, there could be clustering effects in both, but I would say they might be harder to address or really harder to have data that would allow you to address the clustering in aggregate data. Because often what we have is just the aggregate measures or statistics per time period. It's very unlikely that you would have the outcome summarized, say if you had hospitals for every hospital, or you might, I guess, yeah, it's possible, but mostly it's just an overall measure of the outcome at different time points for aggregate data. Power, there could be more power for individual data in general, because for aggregate data, you might only have, again, say the proportion or the rate across time, across different time points. Whereas for individual data, you could have for every individual the specific covariates, and of course that means we have larger sample size for individual data, usually. Can we use generalized linear mixed models in both? Sure, if we're able to identify the clusters in aggregate data, which I would say is not that common. Generalized least squares, sure, can be used in both. Generalized additive mixed models, yes, can be used in both, as long as we have clustering or a way of identifying clusters in the aggregate data. ARIMA or any other models that address serial correlation, most likely they might be more needed again here or any other complex. So this could really be together with the autocorrelation role here. Any questions, any comments? No questions, no comments.
Nothing.
Well, I think we can close this session. Rebecca, are you there?
Yes, I am. Thank you very much. Thanks for attending day one. We hope you enjoyed all the fantastic talks, and please join us for day two, where we'll be focusing on data sources for pragmatic trials.
Okay, great. Thank you all.
Thank you.
Enjoy the rest of the conference.